In this set of videos, we're going to talk about integration in polar, cylindrical, and spherical coordinates. And I'm going to start doing something that I normally don't do. I'm going to give you all of these equations first, and then we're going to talk a little bit about why, and then I'm going to run through some examples. So if we're going to do integration in polar coordinates, notice that this is a double integral, meaning that we're integrating down in R2, and the bounds are going to be in terms of theta and r, because those are the two variables that you use for polar coordinates. So integration is going to function just like you think that it should, except there's going to be this extra red factor of integration r, meaning that whatever function you're dealing with, you're going to have to convert into polar coordinates of r's and thetas, and then you have to multiply that by this red r. It's red on my screen. I don't know if it's red on yours. I'm going to explain where this r comes from in a second, but first let's go through the other formulas. For cylindrical coordinates, recall cylindrical coordinates are in R3, three variable functions in the x, y, z space, or when you convert into cylindrical, they are going to be in the theta, r, and z space. It's going to be just like polar coordinates, because down in the xy plane, you're going to be looking at theta and r, and in the z-plane, z is going to be our regular function z. And all of these messy bounds are just indicating the fact that as you move outward in these integrals, you need to make sure that you're eliminating your functions so that the interior bounds match your z variable. The next ones are r and the next ones are theta. By Fubini's theorem, we are able to mix these up, but we're only able to mix them up so long as the bounds are not functions of a variable that doesn't get taken care of later, right? That's a review of the previous concept. Again, we're going to have this factor of integration r, just like we did here, and I'll explain that in a second. Finally, we also have a way to integrate in spherical coordinates. This is the whole reason why we learned cylindrical and spherical coordinates, to be honest. It's that there are certain things that are really hard to integrate using rectangular coordinates. The algebra gets really messy, the integration gets really messy. So instead, if you convert them into spherical coordinates, sometimes the integration is much easier. Just like before, you need to make sure that your outer bounds match the differential as you go inward. But here, the factor of integration is more complicated than r. The factor of integration is going to be rho squared sine phi. This is something that I'm actually going to have you memorize. There's an optional video that talks about coordinate transformations that explains where this comes from, but that's not something that I'm going to hold you responsible for learning. What I am going to hold you responsible for is having a general idea of why this factor exists, the r and the rho squared sine phi, and also I want you to be able to apply these to be able to compute integration problems that you wouldn't otherwise. So let's get on to the theory. That was a lot of talk. Recall, let's say that we're integrating in polar coordinates. So let's say that I'm trying to compute the area of this arc. And before, when we were talking about rectangular coordinates, our approximations were tiny rectangles, right? And we let those rectangles have a base dx and a height dy, and they got smaller and smaller. And as we took that limit, that's where the integral came from. The same thing is happening here, but instead of visualizing tiny rectangles, we have tiny portions of circles. And notice that in this case, this is not an arc, this rectangular chord region of a circle, I could approximate it by a rectangle, but what would the dimensions of it be? Notice that this dimension right here along the side is change in r. It's the change in radius, right? Because here's a smaller radius, and as I go outward, the radius has grown. This is my difference in radius value. Whereas this inner arc is going to be given by the change in theta times the radius, or r change in theta. Because as my angle theta changes, right, what is the length here? It's going to be the portion that my angle changed times the radius for the whole entire, well, I guess this figure right here. And notice that as we move outwards, like in here for this change in theta, my rectangular approximation is going to be really tiny. Whereas as I move outwards, this R impacts the area of the region. So this is my rough sketch of a geometric description for why we have this extra red factor R. Essentially, all that I'm saying is that as the radius changes, it impacts the area of each of these differentials, and that R takes care of it. There's a longer explanation that involves coordinate transformations in an optional video. So let's actually do some integration. So here's a problem. Suppose I want to integrate the function x plus y over the region R shown below. And from previous techniques, we could come up with the bounds of this region. Notice that I would have to break it up into two different type 1 regions. I would have to be able to describe this outer circular region in terms of y and x, and so there's going to be messy square roots. And that's something that I could try to do, but that's going to be really messy. So instead, I can convert the bounds of this region R into polar coordinates, because polar coordinates describe this region really easily. Notice that in polar coordinates, my radius is between 1 and 2. So for my inner integral, I'm going to let my R values go from 1 to 2. My outer integral is going to describe the angle that's swept out. Theta in this case starts down at 0 because it's exactly at the x-axis and goes up until I hit pi over 2. So these are my bounds in terms of R and theta. This function x plus y I have to convert into polar coordinates in order to be able to compute this. Recall from our previous video that x is going to be equal to r times the cosine of theta, and I can look at triangular geometry to see if I pick a point here, the x-coordinate is going to be the cosine of the angle with a hypotenuse of r, and our y the value of y is going to be equal to r sine theta, again by triangle geometry. The piece that I don't want to miss is that this whole function is multiplied by r. This is our factor of integration. Just because we converted coordinate systems, we need to make sure that we remember that. And our integration is dr d theta. So that's the setup. If you don't want to have a review of integration, you can skip ahead to the next video. Otherwise, I'm going to go ahead and integrate this. We'll see that this red r gets multiplied through each of those terms, so I end up with r squared cosine theta plus r squared sine theta dr d theta. By Fubini's theorem, I could have done the r on the inside or the outside. It doesn't matter, because the bounds are all constant bounds. Even though it looks crazy, these are constant bounds in terms of theta and constant bounds in terms of r. So let's integrate with respect to r. That becomes 1/3 r to the third cosine theta plus 1/3 r to the third sine theta, evaluating r from 1 to 2. And don't forget our outer integral. Let's evaluate this. When I plug in 2 to the third is 8, so I end up with 8/3. And when maybe I'll even factor this out, what I'm doing in my head, becomes 8/3 minus 1/3, all times cosine theta plus sine theta. This is integrated with respect to theta still, as theta goes from 0 to pi over 2. Let's pull out this constant. This is a 7/3 that becomes a constant out front, 7/3. And then I'm going to do this integration. The integral of cosine is sine, and the integral of sine is negative cosine. And I'm evaluating that from theta equals 0 to pi over 2, which is equal to 7/3. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. So that's 1 minus 0 minus the lower bounds. The sine of 0 is 0, and the cosine of 0 is 1. So 1 minus 0 is 1, minus negative 1 is 1, becomes 2, and I end up with 2 times 7/3, or 14/3. And you can check my algebra if you'd like.